This is FRQ number 1 from the Kinematics review packet. The first 10 meters of a 100-meter dash are covered in 2 seconds by a sprinter who starts from rest and accelerates with a constant acceleration. The remaining 90 meters are run with the same velocity the sprinter had after those 2 seconds. So in part A, they asked to determine the sprinter's constant acceleration during those first few seconds. This is going to be a kinematics problem. We're going to use the first equation of motion, and that is going to be equal to delta x is equal to VO, the initial velocity, times t, plus 1/2 AT squared. I chose that one because I know delta x. That's right here. That's the first 10 meters that I'm solving for, or that he ran. I'm solving for A, and time is also known. It's right here. It's 2 seconds. The initial velocity is 0. He started from rest. So this is solvable. I can solve for A. I'll multiply both sides by 2. That becomes 2 times delta x is equal to AT squared. Solving this for t, I divide both sides by A. I get 2 delta x divided by A is equal to t squared. And then I'll just take the square root of both sides. So I get 2 delta x over A is equal to t. Oh, wait, I made a mistake. That's not what I'm going to do. Because I'm not solving for t, I'm solving for a. So I'm going to leave the a on the right. I'll leave it right there and divide both sides by t squared. That becomes 2 delta x divided by t squared. Or I could write it as 2 times delta x, which is 10 meters, divided by the time, which is 2 seconds. But I got to remember to square it. That's going to be 20 over 4. And so 20 over 4 is going to give me 5. And the units are meters per second, or meters per second squared is equal to the acceleration. That's my answer for part A. In part B, they say determine the sprinter's velocity after the 2 seconds have elapsed. I'm going to use the second kinematics equation. This is V final is equal to V initial plus acceleration times time. The reason I chose that one is because the initial velocity is 0. The final velocity is what I'm looking for, and I know now both the acceleration and the time. So VF, the final velocity, is going to be the acceleration, which is 5 meters per second squared, times the time of 2 seconds. And we can see that after 2 seconds, the sprinter reaches a speed of 10 meters per second. And so that's going to be my velocity after the 2-second interval is over. So that's the answer to part B. Part C goes on to ask, hey, what's the total time needed to run the full 100 meters? So the time that I'm looking for, which is the kind of total running time, is equal to time elapsed during part 1, which is the acceleration period. I'll call that TA, plus the time required for the constant velocity time. I'll call that T subscript B, or the constant speed time. Well, we know this one. This is 2 seconds right here. We solved for that. Sorry, it was given in the problem. That's 2 seconds. I just need to figure out how long it takes to run the remaining 90 meters at a constant speed of 10 meters per second, because I now know that. So that's just a velocity equals distance over time kind of question. I'm solving this for time. And I can just kind of multiply both sides by t and divide by v. That becomes time is equal to distance over my velocity. Looks a little funny the way it came out there. And the distance, I'm kind of doing this off to the side, the distance is 90 meters, and the velocity is 10 meters per second. That's my answer, by the way, from part B. And so we can see that the time that it takes then to cover the second constant velocity period is 9 seconds. So if this is 9 seconds and it took me 2 seconds to accelerate, the total time then to run the full 100 meters is 11 seconds. And then finally, on this axis, they want to draw a displacement versus time graph for the sprinter. Well, we know that at 2 seconds, they're going to be at 10, the first 10 meters. So they get to that time in the first 2 seconds, but that has to be a curve. That's going to get curved up because we're accelerated. And then at time 11 seconds here, we're at the 100 meters finish line. And so the second piece is linear. Let's see if I can kind of draw that as straight as I can. Well, that was pretty close. I'm a little bit off, but you get the idea. I'll just make the dot a lot bigger. But this piece here is linear, and the piece at the beginning is quadratic. It's not. And so that's the solution to FRQ number 1 from Kinematics.